Hello, Paul Russo here, and I'm going to use this video to demonstrate the use of the MultiRun program when you want just a single run. Now, normally, if you have just a single run, it's because you have a nice quiet sample and you just collect the data, run it through the ALV, which automatically generates your cumulants output. If you're on top of your game, you remember to do exponential fits at the same time. You pop all that into Harvest, which is pretty much a cut and paste type of program. Boom, you have all your files, including a data set that you can drop into Origin to make pretty files, pretty plots. But there are cases where you want to just a little bit more flexibility, or maybe you forgot to do your one exponential fits at that time. Sometimes you can try to import the data back into the ALV and do it. That sometimes works. But you may also want to avail yourself to the floating baseline cumulants approach that MultiRun uses. So MultiRun does work just fine for a single run, and that's what we're going to demonstrate in this file, in this video. And you'll see that we can do that floating baseline cumulant. All right, so let's go to my bundle file and copy a fresh copy of MultiRun. And remember, we have to make it say SMALS MultiRun only. That's the only thing that work. This is just an Excel file that pops up here temporarily, and then we come here. I did not start with a MultiRun version for toluene, and this is a sample that was run in toluene. This is going to be a sample of polystyrene and toluene. And there it is. We see a pretty nice intensity behavior, reasonably good semi-log type behavior, breaking up a little bit and curving, a little bit curvaceous because this is not a monodispersed polystyrene. Okay, so how do we run just a single run with this? Well, we go back to main. We compute average, which is kind of silly, but that's what we have to do. And when this file was saved, we forgot to adjust the parameters for toluene, but trust me, it's toluene. And let's see, now we'll go to populate export sheet. That's the next step. Kind of fun to watch that run. Now we'll go into multi-exponential fits. And I've been fitting a few of these, so I know I want to start this one off at starting first channel use of 30. And I want to mention a little bit about solver for doing these things. It's important to tighten up your solver. So this is a pretty tight limit. And then I like to use the central derivatives, which is a little slower but better, more accurate. And I like to use multi-start, which tries different starting parameters in search of some sort of really global solution or something that solver at least thinks is a global solution. So that's what we're going to do. And we'll go load the first angle in. And it says solver converged in probability to a global solution. Yay. You can always in these programs look at your residual plots and expand them up a little bit. And you here see that we're only fitting, we have a rapid decay here, which is some combination of correlated after pulsing and I think a little bit of a rapid decay cooperative diffusion mode or something very small building into this solution. But anyway, I guess we really have to expand this to see whether these are working, because ridiculous. Let's try that. So, in the regime where we're fitting, which is where these green lines are, drop down here, it's sort of random errors. I guess we can make that even a little bit more random. So you can see that, in the range where we're actually fitting the data, it's a nice random error. It's also worth looking at how much baseline offset, how much baseline liftoff there is here. That's here. So yeah, it's about a 1 part per thousand baseline liftoff. Okay, so that's one thing you don't get, at least not very easily, in the ALV's version of cumulants. So this is a good reason for using MultiRun for these fits. Although this isn't cumulants, this is one exponential fits, but we will check that again when we get to cumulants. Okay, so let's go ahead and populate some of the others. Load angle 2. Again, global solution found. I think I'm still happy with this range. So we go over here and see what we got. Well, pretty decent behavior. This is behaving still very much like a dilute solution. Nothing really to write home about here, just pretty much standard stuff. You could go ahead and capture, since it seems to be fairly flat, you could actually capture just the average here for the radius. And so in this case, it's just like doing 8 separate experiments all at once, because there doesn't seem to really be a trend to the result. That doesn't hold true as this sample goes to higher concentrations, by the way, which is some interesting polymer physics type thing going on there. Here, let's see, go back up here, we'll start again with 30. And we'll do the cumulants. And we do sometimes see solver encountered an error in the objective cell or a constraint cell. One of the cells in the worksheet became an error value when solver tried certain values for the variable cells. It seems to me like solver sort of stops itself and corrects that. But it's worth having a good look at the quality of the fit here. It is a cumulants fit, so of course the data are going to go tearing off at the end after that cumulant term becomes kind of dominant. We might be fitting too many channels here. It seems like we're getting a nice fit through the data all right though. Residuals plot looks pretty good in our range. Just here on, kind of random. And what about the offset of the baseline? Very small offsets of baseline here, because we also have the mu2 parameter to fiddle around. I find it's, even though solver is programmed to do multi-start, starts with different parameters, it's sometimes helpful to go and just change these a little bit. So let's go ahead and change this one to, okay. I think that will probably not produce anything that you would really see. Maybe in the tail here, let's see what that does. Let's change that back to 0. Well, 0, of course, it doesn't blow up on you. Okay. Let's change it to 5. Now it blows up way too soon. So it was finding about 0.87. We'll put it at 1. And we'll load it again and see if it comes back to 0.87 or whatever it was. Yeah, pretty much. Okay. So I think maybe we don't want to be fitting all those channels, but it doesn't seem to be hurting us much in the range. Doesn't seem to be hurting us. So I think we're just picking up some stuff with the floating baseline. So we'll leave that alone for now. And this is what I'm saying. It's sort of nice to be able to have this sort of dynamic visual interface when you're doing these exponential fits or single multi-parameter nonlinear least squares fit. This is a cumulative fit. Let's see. I don't know if I really want to move back a little bit and include more of that fast decay. Maybe not this angle, maybe the next one. Let's see. Okay. It's not the quietest data. This would be a sample that if we were doing this in a real serious scientific study, we would really get multiple runs and build quieter data. What do I think about that? Do we want to move that back? Let's move it back to 20 at this point. Take a larger range. Which one was that? 7. By the way, if you make your solver less fussy by clicking off multi-start in particular, you won't see these errors, but I think you get the same answers. So anyway, scroll over here, see how we did. Cumulant fit. Yeah, basically the same kind of answer, pretty much flat line type behavior, maybe a little bit more variation. We have more parameters going on here simultaneously, so it's not surprising that it's not as systematic as the one exponential with floating baseline was, but pretty good. Anyway, that is a demonstration of using MultiRun to analyze just a single run. So now we'll save that. And we'll actually remember to rename it. And that's the end of the demonstration.